what I'd like to do is, for our review, I'm just going to run through each of these different topics. And you just sit back and just listen and see if there's a particular topic that you just don't have any clue and don't remember, and then we can just start there. Okay? And there's a gazillion problems here. There's no way we can get through all this. So this is pretty much what we're going to be working on too at our help session. So let me just get started and run through these. And you can just kind of listen, I think would be the best way to do this. So, first one. What is the molar interpretation of a chemical equation? All that is mole bridge. You give them a chemical equation, and it's, they're mole ratios. That's the mole bridge idea. How do you convert a given amount of reactant to product? Well, they always give you grams, right? And then you have to convert those grams of that reactant into what units? Moles, so you can use the mole bridge. And how do you convert grams into moles? What did we use this for? It was called what? What mass? Molar mass. To me, the terminology helps if you use it and you're thinking about solving these problems. We'll use molar mass to convert the grams of that reactant into the moles of that reactant. Then how do you get it into moles of what you're interested in? What was the word? What bridge? Mole bridge. So use the mole bridge to get it into the moles of what you're interested in. Then you got to get back into grams of what you're interested in. Use what again? What mass? Molar mass. So that's pretty much what you got to do, right? Use molar mass to get into moles. Use mole bridge to get into the moles you want. And okay, then use molar mass again. What is a limiting reactant problem? That's where it's pretty much the same as the question right above it, question 2, except you got to do it twice. There's 2 reactants, and they give you the mass of not just one. They give you the mass of both of them. So you convert both of them to the grams of the product that they're interested in, and you have 2 answers. You always pick which ones. Which one do you pick? Because you have 2 answers. One's bigger than the other one. It's the smallest one. It's the smallest one. That was called the limiting reactant problem. How do you predict if a compound is soluble? Right? What was the game plan for that? Oh, it's an aqueous or it's a solid. There's a chart. Now, do I give you that chart? Yes. You just have to know how to use it. The chart is called solubility rules. Right? And I give it to you. You just have to know how to use it. Okay, that's how you predict. There's one particular idea out of that, though, that's going to knock out, I'd say, 50% of your problems. You don't even have to look at that chart. And I harped on this. You put what elements in any compound, it's always aqueous. What were they? Group what? The alkali metals, group 1. Lithium, sodium, potassium, with anything, it's always aqueous. You don't even have to look at the solubility rules. There's so many compounds that are like that. How do you write molecular, ionic, and anionic equations for some common reactions? Do you remember these? I gave you. There's a cheat sheet for this. You follow solubility rules, just like we talked about for precipitation. But then you could generate CO2 gas and H2O liquid. Remember that cheat sheet? So when you're doing that and you identify that common reaction, the first thing you should do is follow that cheat sheet and write down that CO2 gas plus the H2O liquid or whatever the reaction is. And we'll do some of those. How do you determine oxidation numbers? Right? That's a question like this, where I give you a compound and you have to determine the oxidation number of every single one. That was those types of problems. Was there a cheat sheet for that? Or do you have to know it? There's some little steps, and there's a cheat sheet, but you got to know those steps, right? That was kind of for balancing, but for pretty much for these oxidation numbers, you pretty much always realize, oh, oxygen is always what? This is where it always started. -2. Oxygen's always -2. And then you realize, oh, okay, well, I've got 4 oxygens, I've got 1 sulfur, and 1 calcium. They all got to add up to be, all these oxidation numbers have to add up to be what? 0 in this case for calcium sulfate. Okay, that was the other trick. I think those are the 2 tricks, I think. How do you determine oxidizing and reducing agents? Oxidizing agents always get reduced. Reducing agents always get oxidized. So you just have to find some element on both sides, right, and see how it changed. See whether it got reduced or oxidized. And that tells you. It's just determining oxidation states again. And we can do we'll do some of those. How do you balance? So backing up, for determining oxidation numbers, there was no cheat sheet. You just had to know those rules, right? There was no cheat sheet. How do you balance oxidation and reduction reactions? Yeah, now here, was there a cheat sheet? Do I give you a cheat sheet for this? Or do you have to know how to do this? You have to know it. Okay, so what do you do first? You give them this unbalanced oxidation reduction reaction. First thing you do is break it into its half reactions. Use the terminology. It's going to help you. Break it into its half reactions. Next, for each half reaction, balance what? Everything but the O's and H's. Exactly. That's step number 1 for this, for that balancing one half reaction. Step number 2 for balancing the half reaction. Balance the O's by adding H2O. Step 3, balance H's by adding H+. Last step, balance the charge by adding the E negatives, the electrons, to the most positive side by adding H2O. Okay? Balance O's by adding H2O. So know those steps. And then we just had a quiz on this molarity, and I give you those equations, just like we took on the quiz. Okay, so out of all those 9 topics, okay, there's a lot here. We can start right at the top if you want, or if someone has an area of 1 through 9 where, oh gosh, I don't remember that at all, let's start there. Frankie.
The balance and reduction reactions, the basic, acidic,
Yeah, let's jump there. Okay. Compound soluble, reactions, oxidation numbers. There it is. Okay. I've got a bunch. Let's do this one. I don't think we've seen this one before, right? Let's try it. Okay, let's try this one. Break it into its half reactions.
Oh, yeah.
Use the terminology. Break it into its half reactions. Try not to look at your notes. Try to just do this by memory or ask. Balance everything but O and H. Balance O's by adding H2O. Balance H by adding H plus. Balance charge by adding electrons to the most positive side. Wait, this whole thing is a -1 charge. Oh yeah, right here? Yeah, 0. 0. It has a +2. Yeah, +2. So this whole side is +2. This whole side is +4. So this is the most positive side. So you have to get both sides to be the same. It'd be 2 E negatives. The -2 and a +4 would give you a +2. Is that how you balance the manganese half reaction? Hopefully you added 2 electrons to that product side. Right? Okay, you're doing it right if you did that. Keep going. Well, what would you do? See? ClO3 minus goes to Cl2. Are the chlorines balanced? Yep. So then you jump to oxygens. How many O's? How many O's? 2. So I need more O's on this side. And just add 1 of them. If I needed 2, I'd add 2 H2O's.
Okay, so that's why you had only
Yeah, I needed 2 H2O's on top because I need 2 oxygens. But now I screwed up the hydrogens, 2 hydrogens, so I had to put 2 hydrogens over here.
And then you got 2
Because this whole side is +4. You're talking about the chart. This 2? The 2 electrons? Or what are you talking about? Okay, so this whole side is +4. This whole side is +2. Last step is add electrons to the most positive side. This is the most positive side. I need a -2. -2 and a +4 give me +2. Now they're balanced. How did I get the +4? 1 times 0 plus 4 times a +1. Always multiply the coefficient times the charge.
like going across like 2 times. Oh, okay, so
Now remember you're in basic here, so you have some extra work to do. Let's add the top part first. 2 H2Os. Oh, those H pluses cancel. So we don't have to worry about basic. Isn't that nice? Wouldn't this be nice to be on the test? H2Os are gone too. Nice. Doesn't matter whether it's acidic or basic solution. There's no H pluses to worry about. Right? That wasn't as ugly as I was hoping it was going to be. I bet the other one is. Okay, so we can work another one of these, or is there another topic? Oh yeah, right there. This one would be work. There's no way the H plus is going to cancel out. I didn't think they would cancel out in that last one. That's different. Space. So there's my two balanced half reactions. I added 2 electrons to the cyanide half reaction, 2 electrons on the product side, and 3 electrons on the permanganate half reaction on its reactant side. If you end up with electrons on the same side, you know you screwed up somewhere. They're going to be on opposite sides. This whole idea of redox is something is producing electrons, another half reaction is actually reacting with them. That's the whole backbone of all this. That's why they're so energetic. So if it would have said acidic solution, I'm done where I'm at. I end up with having 2 H pluses on the reactant side. I could have quit if it would have said acidic. But it doesn't, Jesus. It says basic, so what do I got to do? It says basic, so I got to convert all these H pluses essentially to water by adding what? OH negative. So wherever I see an H plus, I have to add an OH negative. And if I do it to one side, I better do it to the other, because this is a nice balanced equation. You don't want to mess it up. I have 2 of them, so I have to add 2 OH negatives. So I better do that to this side too. Plus 2 OH negatives. Okay? And you can't leave it like that. This is really how many H2Os? Right? 1 H plus and 1 hydroxide makes 1 water. So 2 of those would make 2 waters. So this whole thing is gone. And I've got 1 water on the other side. So I can cancel him out. He's gone. So I definitely need to rewrite this because it is such an ugly mess. So my final answer would be 3 cyanides and 1 H2O and 2 permanganates goes to 3 these cyano ions. So be clear where your answer is. You don't get points taken off for me grading the wrong thing. And hopefully you're just flying through the exam. You got time to check, right? Why turn in your exam early on questions like this? It's pretty easy to make a silly mistake. Just balance the O's. If the O's are balanced, you got to be good. On the reactant side, I've got 1 O and 2 times 4, 8 O's. So I have 9 oxygens over here, right? Got 9 oxygens. And over here, I've got 3, 2 times 2 is 4, so 4 and 3 is 7, and 2, 9 oxygens. So it's balanced. Okay?
So like the next one, we just say we just stop at the...
Oh yeah, definitely stop at the H pluses, right? Yeah, stop at H pluses if it says acidic. Good. Okay. Go back up. What's another topic that you really feel you need to look at your notes for, but you're not supposed to? Monica, what area? Let's just dump. I'm going to jump to then where the other class said. They had questions on limiting reactant. That's been a while. Right here. Let's try this number 4. Try this number 4. In the above reaction, 5.7 grams of lead-2 nitrate is mixed with 12.9 grams of sodium sulfate. How many grams of sodium nitrate are produced? Okay. where do you start? Yeah, so start with the two reactants, right? Because these guys are both reactants, the lead nitrate and the sodium sulfate. They're all both reactants. Convert them both to grams of NaNO3. And which one's your right answer? Smallest one. Try it. Convert each of those amounts to the product. First step is molar mass to get it into moles of that compound. Then you use mole bridge to get it into the moles of the compound you're interested in. Then molar mass again to get you back to grams of that compound. All right? So you need grams of this on the bottom, molar mass. So you have to add up a lead, 2 nitrogens, and 6 oxygens. Yep. Mm-hmm. Some people did this on the boards this way, right? It's kind of a healthy thing to do because all the units have to work out. Then you just fill in the numbers. Okay. See what I'm doing, what I'm doing? Man, everyone's getting different numbers for the molar mass of lead 2 nitrate. I was cheating, seeing if I didn't have to add it up. You have to add up 1 lead, 2 nitrogens, and 6 oxygens to get that molar mass of lead 2 nitrate. Right? For one of these, 1 lead, 2 nitrogens, and 6 oxygens. There's probably 207.2 lead plus 2 nitrogens, 28, plus how many? 6 oxygens. 6 times 16. Around 331. 331.2, depending on your rounding, right? So you should have somewhere around 331.2 or 331 as the molar mass of lead 2 nitrate. So 1 lead, 2 nitrogens, 6 oxygens. And mole bridge, I have a 2 there and a 1 there. And 1 mole of sodium nitrate, I have about 23 plus 14 plus around 85. Right? Okay. I got about, I don't know, it depends on how, I probably didn't do a very good job on molar masses, but somewhere around 18 maybe. Alyssa, did you get around 18? 16, yeah. What did you have your molar mass of sodium sulfate? Oh my gosh, I'm not even close. It's 142? See, I need glasses so bad. That changes everything. So now it's, you said it's around what? 15.4? Okay. So hopefully you got these 2 answers, right? Which one is the right one? The smaller one. Okay, now what are you supposed to call that smaller one? This, okay, there's limiting reactant. Is this the limiting reactant? No, this is the, what do they call this? Something yield. Something yield. Theoretical yield. This is theoretical yield. Because they might ask for that, right? But it's the same thing. So that's our answer. What is the limiting reactant? What is the limiting reactant? Now, it has to be a reactant. Either it has to be the lead nitrate or the sodium sulfate. It's a lead nitrate. This is our limiting reactant. Okay. But to answer this question, answer is 2.9. What if they would have said, before we jump to B, let's modify this a little bit. What if they would have said, hey, you actually got, I don't know, 0.1 grams of sodium sulfate was obtained. Only. What is the percent yield? How do you handle that? actual over theoretical times 100. Because theoretical is the maximum, so that's always the bottom. So you're going to take actual over theoretical times 100. So it would just be what? 0.1 over 2.9 times 100. Last question. See if how would you handle part B here? How many grams of the excess reactant remain? How would you handle that? Do you remember? Okay. No one remembers how to do this? So the excess reactant is which one? Which compound? The Na2SO4. The sodium sulfate is your excess reactant. There's something of it left over. So the excess is going to be 12.9 grams minus the grams that reacted. The grams of sodium sulfate that reacted. Okay. How do you get the grams of sodium sulfate that reacted? Yeah. You always use the limiting reagent for all calculations, right? We used the limiting reagent, we use a limiting reagent, limiting reactant. We used it to get this answer. We'll use it to get the grams of sodium sulfate that reacted, right? So we'll convert the grams of lead nitrate into grams of sodium sulfate. And at 5.7 grams of lead nitrate, that's a limiting reactant because that's all gone. Totally, that stops everything once it's gone. So that if all that lead nitrate reacted, convert that into grams of sodium sulfate, that's the grams of sodium sulfate that reacted. So then you jump down to the bottom, put that number in right here, and you'll have it. Okay, try it. Convert those grams of limiting reagent, convert the limiting reagent into grams of sodium sulfate. Okay. And you know you screwed up if you got a number bigger than 12.9 because it's not possible. All right, so we'll start with that 5.7 grams. Convert that all the way to grams of sodium sulfate. Oh my gosh, what happened there? Lead nitrate was 331.2. Nitrate is 1. Sodium sulfate is 142. About 2.44 is what I got. About 2.44. So the put in 2.44 right here. Yeah, great. About 10.5 or so. That's how much you wasted just sitting there. Okay. So come by. I'll be glad to work with you on more of these.